Ever stared at a massive, text-heavy syllabus of computer terms and felt completely overwhelmed? Trying to memorize endless pages of technical definitions can make your brain freeze up. The trick is to stop trying to memorize sentences. Instead, we can use simple aesthetic design, things like typography, layout, and color, to map out the information so it mimics how a computer system actually organizes itself. We start by setting up a master header. By writing the main topic in bold, clear typography, you immediately reduce the mental effort it takes to figure out what you are looking at. You give your brain an anchor. This flowchart shows the 4 functions that define every computer system on Earth. You have an input, a feeder of raw information, that moves into processing and storage, the brain of the machine, and finally, that produces an output, the final results. By drawing out this simple visual cycle first, you create a mental framework. Whenever you encounter a new piece of hardware or software later on, you don't have to memorize it in a vacuum. You already have a bucket to drop it into. Let's look at the history of these machines. To make this easy to digest, we can draw a timeline where we shrink our handwriting size to match the shrinking physical size of the computers over the centuries. In the 1800s, an inventor named Charles Babbage designed the conceptual starting point for all of this. His computing engines were purely mechanical. They relied on thousands of hand-cranked metal gears to calculate numbers. By the mid-20th century, we get the first electronic computers. To process basic data, these machines required massive cabinets that filled entire rooms. The technology powering these giant machines were vacuum tubes, fragile glass bulbs that controlled the flow of electricity. Jump forward to the present. Today, machines like India's Param City AI can handle trillions of individual instructions every single second, all while running on silicon chips that fit in the palm of your hand. The physical scale shrank from towering racks of glass tubes down to chips smaller than a coin. Yet the underlying data processing architecture we mapped out earlier stayed exactly the same. So let's map out the hardware we actually touch every day. A clean 2-column grid layout is perfect for this. On the left, we'll use a cool blue color for input devices. Think of these as the raw material feeders, the tools you use to talk to the computer. Your keyboard and mouse go here. But we can also add specialized tools, like a text reading scanner that turns a printed page into a digital file, or the magnetic sensors banks use to instantly read the numbers at the bottom of a check. On the right column, we'll use a bright orange for output devices. This is where the computer talks back to you, delivering a translated, finished product. A monitor is an output device, translating data into millions of colored pixels on a screen. A printer is another, taking a digital file and stamping it onto a physical paper record. By strictly color coding and spatially separating the inputs on the left from the outputs on the right, you remove the need for rote memorization. Your brain recalls the color and the location on the page to remember the function. Right in the center of our layout, we need a high-alert visual priority, like a bold red box, for the Central Processing Unit, or CPU. This is the brain of the operation, doing the actual math. To do its job, the CPU needs a highly structured system for storing and retrieving information. We call this the memory hierarchy. This pyramid diagram illustrates how that hierarchy works. At the very tip, you have registers and cache. These are built directly into the CPU. They offer lightning-fast speeds, but their storage capacity is incredibly limited. The middle tier is RAM, or random access memory. Think of RAM as a temporary workbench. It holds whatever you're working on right now, but it requires a constant stream of electricity to stay awake. If the power goes out, the workbench is wiped completely clean. Finally, we have the broad foundation, hard drives and solid-state drives. This is your permanent filing cabinet. It provides massive amounts of storage space, but it takes the CPU much longer to dig through it. Visualizing memory as a pyramid illustrates the main compromise in computing. As you move down the pyramid, you gain storage space, but you lose processing speed. We now have a beautifully organized grid of physical hardware, but all those chips, screens, and hard drives are useless without a set of instructions telling them what to do. That is where software comes in, specifically the operating system. It acts as the invisible manager that coordinates the memory, tells the processor what to calculate, and directs the input and output flow. Let's pull back and look at our completed visual cheat sheet. All the history, the hardware columns, and the memory pyramid fit perfectly into a single cohesive map. Compare this clear, spatially divided map with the dense, intimidating wall of text from a standard syllabus. An operating system organizes hardware so the computer can function smoothly. By applying those same design principles to your notes, you're building a mental map that matches the machine's logic, making it much easier to recall exactly where each piece of information lives.